Hello everyone, welcome back. I'm your friend Isaac. So today we're going to learn a new series of mathematics, and it's called high school geometry. Did you know the meaning of geometry? Geometry. Well, it's just about the shapes in the real world. All right, let's get into it.
A lot of what geometry is about is proving things about the world. And in order to really prove things about the world, we have to be very careful, very precise, very exact with our language so that we know what we're proving and we know what we're assuming and what type of deductions we are making as we prove things. And so to get some practice being precise and exact with our language, I'm going to go through some exercises from the geometric definitions exercise on Khan Academy. So this first one says, 3 students attempt to define what it means for lines L and M to be perpendicular. Can you match the teacher's comments to the definitions? All right, so it looks like 3 different students attempt definitions of what it means to be perpendicular, and then there's these teacher's comments that we can move around. So we're going to, I guess, pretend that we're the teacher. So Ruby's definition for being perpendicular, L and M, lines L and M, are perpendicular if they never meet. Well, that's not true. In fact, perpendicular lines, for sure, will intersect. So, in fact, they intersect at right angles.
All right, speak of that. Here's the thing you need to know. What is perpendicular? Well, it's just the concept when 2 lines are cross each other and the angle they produced is 90 degrees. Okay, that's how they define the concept of perpendicular.
So that's not going to be correct. And so actually this looks right. Were you thinking of parallel lines? Because that looks like what she was trying to define. If things are on the same plane and they never intersect, then you are talking about parallel lines. I also get Shreya's definition. L and M are perpendicular if they meet at one point and one of the angles at their point of intersection is a right angle. Well, that seems spot on. So let's see. I would say, woohoo, nice work. I couldn't have said it better myself. Now let's just make sure this comment matches for this definition. Abhishek says, L and M are perpendicular if they meet at a single point such that the 2 lines make a T. Well, that's, in a hand-wavy way, kind of right. When you imagine perpendicular lines, you could imagine them kind of forming a cross, or I guess part of, a T would be part of it. But I think this comment is spot on. The teacher's comment, your definition is kind of correct, but it lacks mathematical precision. What does he mean by a T? What does it mean to make a T? Shreya's definition is much more precise. They're perpendicular if they meet at one point, and one of their angles at their point of intersection is a right angle, is a 90-degree angle. Let's check our answer. So let's do a few more of these. This is actually a lot of fun. So once again, we're going to have 3 students attempting to define, but now they're going to define an object called an angle. Can you match the teacher's comments to the definitions? So Ruby, well, these same 3 students, Ruby says the amount of turn between 2 straight lines that have a common vertex. Well, this is kind of getting there. The definition of an angle, we typically talk about 2 rays with a common vertex. She's talking about 2 lines with a common vertex. And she's talking about the amount of turn. So she's really talking about more of kind of the measure of an angle. So let's see what comment here. So you seem to be getting at the idea of a measure of an angle and not the definition of an angle itself. So this is actually right. I would put this one right here. We just got lucky. This was already aligned. So Shreya's definition, 2 lines that come together. So once again, this is kind of the definition of an angle is 2 rays with a common vertex. So 2 lines that come together, this is just intersecting lines. Now when that happens, you might be forming some angles, but I would just say, were you thinking of intersecting lines? And let's see what Abhishek says. A figure composed of 2 rays sharing a common endpoint. The common endpoint is known as the vertex. Yep, that's a good definition of an angle. So Abhishek got it this time. Let's do another one. So 3 students are now attempting to define what it means for 2 lines to be parallel. So now let's match the teacher's comments. So Daniela says 2 lines are parallel if they are distinct and one can be translated on top of the other. All right. So that actually seems pretty interesting. That's actually not the first way that I would have defined parallel lines. I would have said, hey, if they're on the same plane and they don't intersect, then they are parallel. But this seems pretty good, because if you're translating something, you aren't going to rotate it. You're not going to change its direction, I guess one way to think about it. And so if you're translating one, if they're 2 different lines, but you can shift them without changing their direction, which is what translation is all about, on top of each other, that actually feels pretty good. So I'll put that right over there. So Ori says 2 lines are parallel if they are close together but don't intersect. So if you're trying to define parallel lines, it doesn't matter if they're close together or not. They just have to be in the same plane and not intersect. They could be very far apart and they could still be parallel. So this isn't an incorrect statement. You could have 2 lines that are close together and don't intersect on the same plane, and they are going to be parallel. But this isn't a good definition, because you can also have parallel lines that are far apart. And so, actually, I'd go with this statement right here. Part of your definition is correct, but the other part is not. Parallel lines don't have to be close together. So this isn't a good definition of parallel lines. And let's see, Kaori. 2 lines are parallel as long as they aren't perpendicular. Well, that's just not true. Because you can intersect. You can have 2 lines that intersect at non-right angles, and they're not parallel, and they're also not perpendicular. So this is, sorry, your definition is incorrect. This is actually a lot of fun, pretending to be the teacher. Let's do another one. All right. So 3 students attempt to define what a line segment is. And we have a depiction of a line segment right over here. We have point P, point Q, and the line segment is all the points in between P and Q. So let's match the teacher's comments to the definitions. Ivy's definition: all of the points in line with P and Q extending infinitely in both directions. Well, that would be the definition of a line. That would be the line PQ. That would be if you're extending infinitely in both directions. So I would say, are you thinking of a line instead of a line segment? Ethan's definition: the exact distance from P to Q. Well, that's just that's the length of a line segment. That's not exactly what a line segment is. Let's see, Ibuka's definition: the points P and Q, which are called endpoints, and all of the points in a straight line between points P and Q. Yep, that looks.
All right. I would assume that you guys do not know the meaning of segment. Well, just imagine if you have an infinite line, and if you just want one part of your line, for example, from A to B, then I would say this part of your line is a segment of your line. And for this segment, it will sure have a property called length, and it's measurable. You could use some numbers to represent its length. For example, it is 3 centimeters, and so far and so forth. Okay, so that's it. Let's continue.
Looks like a good definition for a line segment. And so we can just check our answer. Looking good. Let's do one more of this. I'm just really enjoying pretending to be a teacher. All right, 3 students attempt to define what a circle is. Define what a circle is. Can you match the teacher's comments to the definitions? Duru: the set of all points in a plane that are the same distance away from some given point, which we call the center. That actually seems like a pretty good definition of a circle. So stupendous, well done. Oliver's definition: the set of all points in 3D space that are the same distance from a center point. Well, if we're talking about 3D space and the set of all points that are equidistant from that point in 3D space, now we're talking about a sphere, not a circle. And so you seem to be confusing a circle with a sphere. And then finally, a perfectly round shape. Well, that's kind of true, but if you're talking about 3 dimensions, you could be talking about a sphere. If you're talking about, if you go beyond 3 dimensions, hypersphere or whatever else. In 2 dimensions, yeah, perfectly round shape. Most people would call it a circle, but that doesn't have a lot of precision to it. It doesn't give us a lot that we can work with from a mathematical point of view. So I would say, actually, what the teacher's saying, your definition needs to be much more precise. Duru's definition is much, much more precise. The set of all points that are equidistant from in a plane that are equidistant away from a given point, which we call the center. So, yep, Carlos could use a little bit more precision. We're all done.
Nice teaching. So by doing this kind of exercise or learning, we could easily master those mathematics concepts without hard understanding problem. That's good. Then we're gonna do an introduction to the rigid transformation. I know the meaning of transformation, but I don't know the word rigid.
Rigid transformations.
Rigid transformations. Let's get into it.
Probably used to the word in everyday language. What I hope to introduce you to in this video is the notion of a transformation in mathematics. And you're probably used to the word in everyday language. Transformation means something is changing. It's transforming from one thing to another. So what would transformation mean in a mathematical context? Well, it could mean that you're taking something mathematical and you're changing it into something else mathematical, and that's exactly what it is. It's talking about taking a set of coordinates or a set of points and then changing them into a different set of coordinates or a different set of points. For example, this right over here, this is a quadrilateral. We've plotted it on the coordinate plane. This is a set of points, not just the 4 points that represent the vertices of the quadrilateral, but all the points along the sides too. There's a bunch of points along this. You could argue there's there are an infinite number of points along this quadrilateral. This right over here, the point x equals 0, y equals -4. This is a point on the quadrilateral. Now, we can apply a transformation to this. And the first one I'm going to show you is a translation, which just means moving all the points in the same direction and the same amount in that same direction. And I'm using the Khan Academy translation widget to do it. So let's translate. Let's translate this, and I can do it by grabbing onto one of the vertices. And notice I've now shifted it to the right by 2. Every point here, not just the orange points, has shifted to the right by 2. This one has shifted to the right by 2. This point right over here has shifted to the right by 2. Every point has shifted in the same direction by the same amount. That's what a translation is. Now I've shifted, let's see, if I put it here, every point has shifted to the right one and up one. They've all shifted by the same amount in the same direction.
All right, here he just introduced to you guys a new word called translate, right? So in normal life, as I would think that translate just means you have to translate one kind of language to another language, for example, Chinese to English or English to Spanish or something like that. But here, what he is talking about is that the translate could mean that you move all those points in a shape to another place with the same direction and the same amount. That's totally a new meaning for the word of translate.
That is a translation, but you can imagine a translation is not the only kind of transformation. In fact, there's an unlimited variation. There's an unlimited number of different transformations. So, for example, I could do a rotation. So I have another set of points here that's represented by quadrilateral, I guess we could call it CD or BCDE, and I could rotate it. And I would rotate it around a point. So for example, I could rotate it around the point D. So this is what I start with. Let me see if I can do this. I could rotate it like, actually let me see. So if I start like this, I could rotate it 90 degrees. I could rotate 90 degrees. So I could rotate it like, that looks pretty close to a 90-degree rotation. So every point that was on the original or in the original set of points, I've now shifted it relative to that point that I'm rotating around. I've now rotated it 90 degrees. So this point has now mapped to this point over here. this point has now mapped to this point over here. And I'm just picking the vertices because those are a little bit easier to think about. This point has mapped to this point. The point of rotation, actually, since D is actually the point of rotation, that one actually has not shifted. And just so you get some terminology, the set of points after you apply the transformation, this is called the image of the transformation. So I had quadrilateral B, C, D, E. I applied a 90-degree counterclockwise rotation around the point D. And so this new set of points, this is the image of our original quadrilateral after the transformation. And I don't have to just, let me undo this, I don't have to rotate around just one of the points that are on the original set, that are on our quadrilateral. I could rotate around the origin. I could do something like that. I notice it's a different rotation now. It's a different rotation. I could rotate around any point. Now let's look at another transformation, and that would be the notion of a reflection. And you know what reflection means in everyday life. You kind of imagine the reflection of an image in a mirror or on the water. And that's exactly what we're going to do over here. So if we reflect across a line. So let me do that. So this, what is this? 1, 2, 3, 4, 5. This not irregular pentagon. Let's reflect it. And to reflect it, let me make a line like this. I could reflect it across a whole series of lines. Whoops, let me see if I can. So let's reflect it across this. Now what does it mean to reflect across something? One way I imagine is if this was, we're going to get its mirror image, and you kind of imagine this as kind of the line of symmetry, that the image and the original set of the original shape, they should be mirror images across this line. We could see that. Let's do the reflection. There you go. And you see we have a mirror image. This is this far away from the line. This corresponding point in the image is on the other side of the line, but the same distance. This point over here is this distance from the line, and this point over here is the same distance, but on the other side. Now all of the transformations that I've just showed you, the translation, the reflection, the rotation, these are called rigid transformations. And once again, you can just think about what does rigid mean in everyday life. It means something that's not flexible. It means something that you can't kind of stretch or scale up or scale down. It kind of maintains its shape. And that's what rigid transformations are fundamentally about. If you want to think a little bit more mathematically, a rigid transformation is one in which lengths and angles are preserved. You can see in this transformation right over here, the distance between this point and this point, between points T and R, and the distance between their corresponding image points, that distance is the same. The angle here, angle RTY, the measure of this angle over here, if you look at the corresponding angle in the image, it's going to be the same angle. So you might, and the same thing is true if you're doing a translation. You can imagine these are kind of acting like rigid objects. You can't stretch them. They're not flexible. They're maintaining their shape. Now, what would be examples of transformations that are not rigid transformations? Well, you can imagine scaling things up and down. If I were to scale this out where it has maybe the angles are preserved, but the lengths aren't preserved, that would not be a rigid transformation. If I were to just stretch one side of it, or if I were to just pull this point while the other points stayed where they are, I'd be kind of distorting it or stretching it. That would not be a rigid transformation. So hopefully this gets you, it's actually very, very interesting. I mean, when you use an art program or actually you use a lot of computer graphics or you play a video game, that most of what the video game is doing is actually doing transformations, sometimes in 2 dimensions, sometimes in 3 dimensions. And once you get into more advanced math, especially things like linear algebra, as a whole field, it's really focused around transformations. In fact, some of the computers with really good graphics processors.
All right. What he was talking about is a transformation, right? And what he said is true. Yeah, for sure. And no matter 2D or 3D, what those programs generally doing is to do the transformation. And speak about the word rigid. In the Unity 3D, they have a component called a rigid body. Yeah. What does this body do is to, like I said, to move that object or to doing some collection clashing with other object while preserve the object's original shape and size and so on. Well, there's another definition called dilation. Intro. What is that? What is what is that word?
In previous videos, we started talking about the idea. In particular, we talked about rigid. So, for example, you can shift something. This would be a translation. So the thing that I'm moving around is a translation of our original triangle. You could have a rotation. So that thing that I translated, I am now rotating it, as you see right over there. And you can also have a reflection. The tool that I'm using doesn't make reflection too easy, but that's essentially flipping it over a line. But what we're going to talk about in this video is a non-rigid transformation. And what makes something a rigid transformation is that lengths between points are preserved. But in a non-rigid transformation, those lengths do not need to be preserved. So for example, this rotated and translated triangle that I'm moving around right here, in fact, I'm continuing to translate it as I talk, I can dilate it. And one way to think about dilation is that we're just scaling it down or scaling it up. So for example, here, I am scaling it down. That is a dilation. Or I could scale it up. This is also a dilation. We're even going on.
All right, let me just do a translation about the dilation. Oh, that's how they call that word, dilation.
Dilations.
All right, it's just a word that represents a process of scaling up or scaling down an image or object or shape. Alright, then I think we probably have done the understanding about the translation. But what about the rotation? He also talked about the rotation kind of stuff. And I guess you know that. And here's another one called reflection and dilation. Oh, let's say he just talked about almost every concept that you could encounter. But let's say since we have time, so let me just watch one more video.
We're asked to plot the image of quadrilateral ABCD, so that's this blue quadrilateral here, under a reflection across the x-axis. So that's the x-axis. And we have our little tool here on Khan Academy where we can construct a quadrilateral. And we need to construct the reflection of triangle ABCD. And so what we can do is, let me scroll down a little bit so we can see the entire coordinate axis. We want to find the reflection across the x-axis. So I'm going to reflect point by point. And actually, let me just move this whole thing down here so that we can see what is going on a little bit clearer. So let's just first reflect point. Let me move this a little bit out of the way. So let's first reflect point A. So we're going to reflect across the x-axis. A is 4 units above the x-axis. 1, 2, 3, 4. So its image, A prime, we could say, would be 4 units below the x-axis. So 1, 2, 3, 4. So let's make this right over here A prime. I'm having trouble putting see if I move these other characters around. Okay, there you go. So this is going to be my A prime. Now let me try B. B is 2 units above the x-axis, so B prime is going to have the same x-coordinate, but it's going to be 2 units below the x-axis. So let's make this our B. So this is our B right over here. Now let's make this our C. C right here has the x-coordinate of -5 and a y-coordinate of -4. Now C prime would have the same x-coordinate, but instead of being 4 units below the x-axis, it'll be 4 units above the x-axis. So it would have the coordinates -5, +4. So this is going to be our C here. So this goes to -5, 1, 2, 3, +4. And then last but not least, D. And so let's see. D right now is at -2, -1. If we were to reflect across the x-axis, instead of being 1 unit below the x-axis, we'll be 1 unit above the x-axis, and we'll keep our x-coordinate of -2. And so there you have it. We have constructed the reflection of ABCD across the x-axis. And what's interesting about this example is that the original quadrilateral is on top of the x-axis. So you can kind of see this top part of the quadrilateral gets reflected below it, and this bottom part of the quadrilateral gets reflected above it. And then you can see that indeed they indeed do look like reflections flipped over the x-axis.
Interesting. Let's have a look at, let's say, yeah, this one.
We are told that triangle n prime is the image of triangle n under a dilation. So this is n prime in this red color, and then the original n is in this blue color. What is the center of dilation? And they give us some choices here. Choice A, B, C, or D is the center of dilation. So pause this video and see if you can figure it out on your own. So there's a couple of ways to think about it. One way, I like to just first think about, well, what is the scale factor here? So in our original n, we have this side here. It has a length of 2. And then once we dilated it and used that scale factor, that corresponding side has a length of 4. So we went from 2 to 4. So we can figure out our scale factor. Scale factor is equal to 2. 2 times 2 is equal to 4. Now, what about our center of dilation? So one way to think about it is pick 2 corresponding points. So let's say we were to pick this point and this point. So the image, the corresponding point on n prime, is going to be the scale factor as far away from our center of dilation as the original point. So in this example, we know the scale factor is 2. So this is going to be twice as far from our center of dilation as the corresponding point. Well, you can immediately see, and it's going to be in the same direction. So actually, if you just draw a line connecting these two, there's actually only one choice that sits on that line, and that is choice D right over here as being the center of dilation. And you can also verify that, notice, this first point on the original triangle, its change in x is 2, and its change in y is 3, 2, 3, to go from point D to that point. And then if you want to go to point D to its image, well, now you got to go twice as far. Your change in x is 4, and your change in y is 6. You could use the Pythagorean theorem to calculate this distance and then the longer distance. But what you see is that the corresponding point is now twice as far from your center of dilation. So there's a couple of ways to think about it. One, if you connect corresponding points, your center of dilation is going to be on a line that connects those 2 points, and that the image should be the scale factor as far away from the center of dilation. In this case, it should be twice as far from the center of dilation as the point that it is the image of dilation.
Okay, so in this video, he just introduced us a concept called the center of dilation. Well, what is the center of dilation? You probably have never heard it before, but now you know it, that it's just a point where for each point you connect this central point to your object. For example, this one. They will have the same scale ratio or scale factor for the 2 objects. For example, the length of this, if it's 4, then the length of this would be just 2. I hope you understand that. But I think that this is probably not that useful because I have never made it when I doing the game development or the UI developments. Okay, guys, I think this is the end for this unit of mathematics learning. And I hope you guys enjoy it, and I will see you guys in the next video. Bye!